A paper just dropped in Science Advances, and it might have settled a 50-year-old argument about whether Mars has lightning. Not ancient Mars, not theoretical Mars, Mars right now. For decades, every single time scientists went looking for electrical discharges on Mars, they came up empty. Billion measurement surveys, multi-year radar campaigns, ground telescopes pointed at the planet during massive dust storms. Nothing. Over and over again, nothing. Mars seemed electrically dead. And then a Czech physicist named František Němec sat down with 108,418 recordings from NASA's MAVEN orbiter and started scrolling through them, one by one, by hand. Because as his colleague put it, you have to do this visually. The noise in the data is too messy for a machine to sort through. And out of all those recordings, he found exactly one signal. Recorded on June 21st, 2015, 349 kilometers above the Martian surface, on the night side of the planet, lasting about 0.4 of a second. And that single blip might be the most important sound Mars has ever made. So what did he actually find? Something called a Whistler wave. And to understand why one whistler changes everything, you need to understand what a whistler actually is. When lightning strikes anywhere, not just on Earth, the discharge blasts out electromagnetic radiation across a huge range of frequencies. Some of those radio waves, the really low-frequency ones, can escape upward through the atmosphere into the electrically charged plasma above. And plasma does something strange to radio waves. It makes higher frequencies travel faster than lower ones. So what started as a single instantaneous burst gets stretched out in time. The high-pitched part of the signal arrives first, and the low-pitched part arrives later. If you converted it to sound, you would hear a descending tone, like a whale call fading into the deep. That descending sweep is the whistler, and it is unmistakable. It is lightning's fingerprint written in radio waves. This is not a new concept. British radio operators during World War I first heard these eerie whistling sounds on their military equipment. Nobody could explain them. It took until 1953 for a physicist to prove that what they were hearing were lightning strikes, transformed by Earth's plasma into these weird descending tones. A Stanford researcher who spent decades studying them described the sounds as, quote, weird, strange, and unbelievable as flying saucers. Since then, whistlers have become the gold standard for confirming lightning on other worlds. We use them to confirm lightning on Jupiter, on Saturn, on Neptune. If you find a whistler, you have found lightning, period. And now, for the first time, we have one from Mars. But wait, why was this so hard? Why did it take over a decade of MAVEN data and 100,000 recordings to find a single event? This is where Mars gets really annoying. Earth has a nice global magnetic field, one big dipole wrapping around the entire planet. Lightning-generated whistlers can travel along those field lines like signals running through a cable. Clean, predictable, detectable. Mars has no global magnetic field. Its core cooled and solidified billions of years ago. The dynamo shut down. What is left are patches, scattered chunks of magnetized rock in the crust, mostly in the southern highlands, that still hold a fossilized memory of the field Mars used to have. Think of them less like a magnetic blanket and more like magnetic puddles sprinkled across a parking lot. For a whistler to propagate from the Martian surface up to an orbiter, it needs to thread through one of these tiny magnetic patches. The field lines have to connect from near the surface up to where the spacecraft is flying. The spacecraft has to be over the right patch, at the right altitude, on the night side because solar radiation compresses the ionosphere during the day and blocks these waves. And a powerful enough electrical discharge has to happen at that exact location at that exact moment. The authors calculated that fewer than 1% of all the wave recordings MAVEN ever took were even made under conditions where detecting a whistler was physically possible. Fewer than 1%. So finding one event is not a sign that lightning is rare on Mars. It might be a sign that we are almost never looking in the right direction. That is a really important distinction. It is the difference between a quiet planet and a planet we have barely been listening to. Now, the team did not just see this signal and publish a paper the next week. They spent a full year confirming it. A PhD student named Katarzyna Rosica built a simulation that combined Earth whistler propagation models with realistic Martian ionospheric chemistry and those patchy crustal magnetic fields. The model predicted that higher frequency components of the signal would be absorbed during transit through Mars's plasma, while lower frequencies would arrive with a specific delay pattern. The actual MAVEN data matched those predictions almost perfectly. When they corrected for signal losses during propagation, the estimated energy at the source was comparable to a strong lightning discharge on Earth. Not a tiny spark, a serious discharge. But this paper did not land in isolation, and that matters a lot. 3 months earlier, in November 2025, a completely different team published a completely different kind of evidence in the journal Nature. Using the Perseverance rover's microphone, a microphone that was originally designed to listen to a laser zapping rocks, they captured 55 electrical discharge events over 2 Martian years. 16 of those happened when dust devils passed directly over the rover. Some of them even included a tiny acoustic shock wave after the electromagnetic pop, a miniature clap of thunder, on Mars. So now we have 2 totally independent lines of evidence from 2 totally different instruments using 2 totally different detection methods. One from orbit, one from the ground. The orbital whistler suggests powerful discharges, comparable to strong Earth lightning. The surface detections are smaller, more like the static shock you get from a doorknob, but real and frequent. And here is what ties them together. Mars's thin atmosphere, which is about 1% the density of Earth's, actually makes electrical discharges easier, not harder. On Earth, dust particles rub together in desert storms all the time, but rarely produce actual sparks because the thick atmosphere raises the voltage threshold for breakdown. On Mars, that threshold is much lower. Less air means less resistance. The charge builds up from dust grains colliding inside dust devils and storms, and it does not need to accumulate nearly as much before it arcs. So the planet with the thin, seemingly dead atmosphere turns out to be electrically touchy, easy to spark. Now let me be honest about what we do not know and where the skepticism is warranted. First, this is one event, one whistler. That is a sample size of 1. It is enormously suggestive, especially combined with the Perseverance data, but it does not give us a rate. How often? Where? During which seasons? We cannot answer any of that yet. Second, Whistler mode waves exist on Mars that have nothing to do with lightning. MAVEN has detected Whistler mode chorus waves generated by electron interactions in the magnetosphere. So the paper has to convincingly demonstrate that this specific signal has the time-frequency dispersion pattern of an impulsive source, a lightning-like event, and not just some ambient plasma process. The authors argue they have done this, and the propagation modeling supports them. But with a single event, there is always a lingering question. Third, there is the standard single event problem: spacecraft interference, instrument glitches. These are real concerns, and the authors apparently spent a year doing artifact checks. That is reassuring, but until we get a second independent detection from orbit, a certain level of caution is appropriate. Fourth, the researchers are careful with their language, and we should be too. They call this a lightning-like electrical discharge, not lightning, because the measurement shows a sudden release of low-frequency electromagnetic radiation. It does not show the visible flash. It does not show the discharge channel. Some of those things might look very different on Mars, or might not happen at all in the same way. The lead author put it well. He said that in the thin atmosphere of Mars, some of these effects may differ significantly from what we know on Earth. So where does that leave us? Somewhere between a strong hint and a confirmed detection, which in planetary science is actually a huge step. Let me give you the historical context for why this matters so much. Scientists have suspected Mars might have lightning since the Viking era in the 1970s. The landers saw dust storms and dust devils, but carried no instruments to detect electrical activity. It was a hypothesis with no way to test it. In 2006, a team at the University of Michigan thought they had caught something. Using a 34-meter deep space network dish, they detected unusual microwave emissions from Mars during an intense dust storm and interpreted them as evidence of Schumann resonances driven by lightning. But a follow-up study using the Allen Telescope Array traced similar signals to terrestrial radio interference. The result was never confirmed. Then came the massive null result. The Mars Express Orbiter's radar instrument conducted a nearly 13-year search across over 1 billion measurements looking for lightning-related radio pulses at megahertz frequencies. It found nothing. Not during calm periods, not during the biggest dust storms. For a lot of researchers, that was the nail in the coffin. But it turns out everyone was looking wrong. They were searching for impulsive radio bursts punching straight through the ionosphere at high frequencies. The MAVEN team's insight was to look for something fundamentally different. Dispersed Whistler waves threading through those patchy crustal magnetic fields at much lower frequencies. Nobody had tried that before. Not because the physics was unknown, but because the geometry seemed too improbable. Well, improbable happened. And there is one more piece of this story that I think will stick with you. In 1971, the Soviet Mars 3 lander became the first spacecraft to successfully soft land on Mars. It touched down during a massive, planet-wide dust storm. 90 seconds after landing, it began transmitting. 20 seconds later, it went permanently silent. Just 20 seconds. They got back one partial image, gray, featureless, almost no light. Then nothing. The official cause of failure was listed as unknown, possibly related to the dust storm. Planetary scientist Ralph Lorenz has raised an interesting question about that event. Something changed in 20 seconds. Could it have been an electrical discharge? We now know that the kind of dust storm Mars 3 landed in is exactly the kind of event that produces electrical activity. The phenomenon that may have been confirmed 54 years later could have claimed its first victim on the very first landing. Now, why should any of this matter beyond just being cool? Because lightning does chemistry. The famous Miller-Urey experiment in 1953 showed that electrical discharges in an early Earth-like atmosphere could produce amino acids, the building blocks of proteins. If similar discharges happen on Mars, even in its current carbon dioxide-dominated atmosphere, they drive reactions. Lightning and carbon dioxide-nitrogen mixtures efficiently produces nitric oxide, which fixes nitrogen, a process critical for biology. It also produces hydrogen cyanide and formaldehyde under certain conditions, both considered essential precursors for RNA world chemistry. But there is a twist that cuts both ways. Those same electrical processes also generate hydrogen peroxide and potentially perchlorates, compounds that aggressively destroy organic molecules. So Martian lightning might simultaneously create the precursors for life and the chemicals that tear them apart. It is a complicated equation, and we are only beginning to write it. For future astronauts, the risk seems manageable. The researchers do not think anyone is going to get struck by a Martian lightning bolt. But triboelectric charging of suits and equipment during dust storms is a real engineering concern. Mars has a low breakdown voltage, which means static buildup on hardware could cause unexpected discharges that damage sensitive electronics. Something to think about as we design habitats and spacesuits for the surface. And there is a bittersweet edge to all of this. NASA lost contact with MAVEN in December 2025, just weeks before this paper was published. The spacecraft appears to be spinning unexpectedly, and recovery attempts are ongoing, but the situation looks grim. The instrument that captured this historic signal may never make another measurement. It gets worse. The Czech team behind this discovery also built a dedicated lightning detector for ESA's Rosalind Franklin rover mission, intended for the Russian-built landing platform. After Russia's invasion of Ukraine, ESA severed the partnership and dropped the instrument. The scientists recently got their hardware back, but it will probably never see Mars. The best hope now is an ESA mission called MAVEN that could launch in 2037 at the earliest, over a decade away. Meanwhile, Perseverance keeps listening from the ground, but its location in Jezero crater only experiences about 5% of the dust devil activity seen in the most active Martian regions. The real electrical action might be 20 times more intense than anything we have measured so far. So what we have right now is a single descending whistle, extracted from over 100,000 recordings through years of painstaking work, confirmed by a year of modeling, arriving from 349 kilometers above the Martian night, backed up by 55 small cracks and pops recorded by a microphone that was never designed to hear them. Two completely different instruments, two completely different scales, both saying the same thing. Mars is not electrically dead. It might never have been. And the spacecraft that proved it just went silent. Almost like the planet has a sense of humor about these things. Want more of the latest science discoveries that keep rewriting what we thought we knew? There is always another signal hiding in the noise.